that given this system that we have, it's a big monolithic system. So, and at one point, let's just say that our app gets more high traffic, people start loving it, and then we need to expand. Before we talk about expanding geographically, let's just talk about expanding in terms of our user base within the geography that we currently serve. And there, just for whatever reason, let's just say that within San Jose, the population grows to 100 million, or even just like 200 million people just in San Jose. So before expanding to other geographies, we're going to just expand within San Jose. Clearly, this monolithic system doesn't work. So how are we going to go about expanding it? And maybe we can talk about different architecture as well as breaking it down into microservices, or whether any other approach that you might think is important here.
Yeah. Do we also expect the driver number to increase significantly?
Yes. So the driver number is going to increase as well as the user number, and let's also assume that we're not going to be able to design the system from scratch, because we put so much engineering resources to design this. So we're just going to talk about scaling the existing system and how we're going to gradually scale it up.
Yeah, and incremental changes.
Cool. Right, as opposed to just breaking down the entire system and starting from scratch.
Yeah. So that's a great question, and thank you for suggesting that incremental approach. That's important. So splitting a monolithic application can be really challenging, and we kind of need to talk about domains. In this world, we can think of a user domain, things that user. I guess user domain and a driver domain. Those are very obvious things that stand out. But by user domain, I want I'm talking about user side of the right domain. There's also another bunch of other possible domains, thinking about user sign up, driver sign up, and their life cycle in this system, which are not high traffic compared to the other aspect of the application, not high traffic aspects of the system. So splitting this would be, first of all, at the API level. We need to, at that point, once we realize that we need to scale, I'm really confident that the API here at the monolithic applications entrance will probably not be suitable to scale, or we may want to revisit that in the same scope. So we could start thinking about a containerized application where a user service or a user write service starts to appear and needs the ability to horizontally scale. And we could use Kubernetes kind of a system, it's actually de facto standard to control and schedule and manage the containerized application here.
Mm-hmm.
Usually there are several layers of load balancers. In this example, if you are just living in San Jose, there could be a single layer of load balancer, service mesh, so to say, where it parses the request that coming from the user, and looking at the path components of the URL, it recognizes that it's a service that's falling into the user domain, knows to the service mesh knows which user domain services are running and alive right now, which is part of the value proposition of a service mesh. Working closely with the Kubernetes API layer, the service mesh can determine, with the help of Kubernetes API layer, which services are alive and ready to receive traffic. And I can talk about, if you want, how that actually works and fits all together.
Yeah, that's actually, talk more about that.
Yeah. So I know a disgusting amount of that. Whenever a service comes up in the Kubernetes ecosystem, its config is described a liveness probe and a readiness probe. Right? A readiness probe signifies that, and these are some code the Kubernetes ecosystem executes on that service. to determine whether it's ready and whether it's live. I think the readiness probe applies more to this question. Once the readiness probe returns true to the Kubernetes ecosystem, the controller running on this node that schedules this container ended up being scheduling talks to the Kubernetes API servers. And the Kubernetes API server has various abstractions, like a pod abstraction, a service abstraction. Eventually, using these abstraction layers, a Kubernetes API server maintains a list of something called endpoints for each service that has a well-known name. So user service will have a particular set of endpoints. Endpoint is like a port and host pair. The service has a name, like user domain service. And then the service mesh implementation knows how to, like, quote unquote, watch this list of endpoints, literally using the essentially etcd's watch endpoint notification mechanism eventually to match to that. etcd is the storage behind Kubernetes. So using that, the service mesh can get notified whenever a new pod comes in. It passes its own readiness check, and that information propagates all the way to Kubernetes API server to etcd, comes back to the service mesh. Service mesh updates its own tables according to the new port and host, and whenever the new request comes according to its service, like traffic distribution algorithm, it can be round robin, it can be something more fancy. It chooses which pod the traffic will go to, and hence somehow the HTTP packets, the bytes, eventually end up in the network interface of this process.
So can we talk a little more about the load balancer and the interaction
between load balancer and what?
Yeah, so the actual interaction between the load balancer and the client side, and how that translates into the server side. So you've briefly talked about round robin approach, and then can we talk about different approaches here?
Just to be sure, the user is not aware of what is going on, which strategy is used there. So eventually there's a list to split the traffic through, and like some traffic load balancers here, like we are talking about Envoy, HA proxy, what else is there, like Nginx kind of a service that can be used here, there's Apache traffic. So what is that project's name? The Apache has something as well. So there's a list and you need to make a decision. The simplest decision is just like choose the next one that you haven't chosen. But the more sophisticated load balancer can maintain some additional state. How much connections are there on the other side, and can choose the least amount of connections the other side has, and that will get more pressure, incoming pressure. Another algorithm is just like random, choose one, whichever, doesn't care, and like rely on your random number generator. Another algorithm, like a little bit more complex one, is you also maintain state how long it took for a particular endpoint to process the request, and then choose the one that is known to process the most recent requests in a shorter duration than the other ones. There are other approaches where you just maintain some additional state about the load on the other side. How many, I mentioned connections, you can just look at CPU.
So for this
there as well.
For this specific use case, like as a designer, what would you choose?
What would I choose? That's a difficult question. So I would spend a lot of time so we are talking about hundreds of millions of traffic, right? We are talking about lots of traffic. So yeah, I cannot do that choice independently.